right, so continuing on with dynamics examples, this is for class 8. We're going to use the same example that we did from, I believe, class 6, right? But we're going to use energy methods instead, where we have this 50-pound force that's being applied to this block. And the block weighs 25 pounds. And it starts from rest, and it's on a 25-degree slope. It's got a coefficient of static friction is 0.25 and kinetic friction is 0.2. Right? We're going to assume it moves, so we'll only use the kinetic coefficient friction. And the force is applied with a 15-degree angle right here. We want to find the distance up the slope when this block reaches 3 feet per second right here. So what we want to do to start off with this right here, and then what I generally like to do is to write out the equations that I need. But actually for this one, I'm going to need to know what the friction force is going to be. So I actually did do a free body diagram and inertial body diagram as part of this right here. I don't necessarily have to do the inertial body diagram here, because I'm going to go X right here, and I'm only going to go in the Y direction. Do I care? So here is my weight being applied to the thing, and here is my normal force, Fn. And we knew with our friction force, we'll put it on there, even though we don't actually need it. And we're putting up here is our angle of this, and here is our angle of this, and we have a force that's actually being applied right there. So that's our P. Here is our theta 2. Here's our theta 1 right in there. Keeping track of this. Here's our mass times acceleration going upwards, and that's in the x prime direction. So the sum of the forces in the y prime direction is mass times acceleration in the y prime, but that happens to be 0 right here. And here is where positive y prime is going right here. So writing this thing out for the y prime direction, we see that we're going to have a negative p times the sine of theta 1 plus theta 2. And then we're also going to have a negative w times the cosine of theta 1 right here, because that's the theta 1. But then we're also going to have Fn. So we could solve for Fn, and that was the point of what we were trying to do here. And I get like, okay, so the P is 50, the sine of, let's see, that was 25 plus 15, and then the weight of the thing was going to be 25, so 25 pounds, and then the cosine of 25 degrees, and what we end up with is 54.80 pounds. That's what we got in the last class. We did that so that we could find what the friction force was going to be. So we take the 0.2 times that 54.80, and what we're left with is a 10.96 pounds. All right, so one good thing, I sometimes I'll draw it onto here, is to like draw up our states right here. This is going to be state 1 and this is state 2, and to trying to figure out a datum right here. So we'll go like this right here, and is going to go right here. So we'll call this the datum. So this distance y2 is going to be the one that we want to find. It's often better actually to just draw it through the center of gravity, but you'll see that it's these positions are the same. So the center of gravity moves the same as this bottom corner. Whatever seems to be a convenient place to take it is a good idea, but just making sure that it's consistent between the two places. And so that vertical distance, that y2, is really going to be the delta s that I'm calling it. I call it right here, times the sine of theta 1. All right, so now this is actually what I will often, for many problems, I didn't this time, will do first, is I will write out this main equation and then start trying to populate it. So KE1, it starts from rest, so it's 0. PE1, well, we established this is the datum. This is starting, so it's starting at 0. The U1 to 2 is the external forces that are happening onto there. So there's two external forces. One is this force right here that's being applied. But remember, it's only the force that's in the direction of its motion right here, right? So it's actually going to be this force times the cosine of theta 1 plus theta 2 is going to be the force that's going to be multiplied by the delta S right here. So we go P is the force times the cosine of theta 1 plus theta 2. But also, we have friction force that's opposing the direction right there. So it's going the opposite. And oh, I forgot to put in the delta S right there, right? So this is the external work that's by this force. But now we have to subtract out the friction times delta S right in there. And now we want to have what the kinetic energy at state 2 is. Well, that's actually kind of where we're being asked what we were told what this velocity is going to be, right? So this we were said that's going to be 3 feet per second. So that's something we know. And then the potential energy at state 2 is mgy2, and we just wrote up above that was mg times. And by the way, it might be easier for us to write it in this case because we were given the weight of the thing. It's just weight times y2, and so we're going to have weight times delta S sine of theta 1. So now we just fill in all the blanks right here. 0 is a placeholder. 0 for here is a placeholder. We're going to have P cosine of theta 1 plus theta 2 delta S minus Fs delta S equals 1/2 m v2 squared, and then plus a w delta S sine of theta 1. And we could plug numbers into all these. I guess I kept it going. I'm looking at my time. We had 50 times the cosine of 25 plus 15 times delta S, and then minus our 10.96 times delta S, 1/2. We got to make sure this thing weighs 25 pounds, but we got to use slugs, 32.2 right in there, and we know that it's 3 feet per second squared, and I ran out of room down here. I put the weight is 25. The delta S is what we don't know, and then the sine of 25 degrees. So we have a lot of things going on here, but we can find out a delta S is going to be 0.2083 feet, and that's equal to 2.5 inches, which is the same thing we got from the example that we did in the previous, I think it was class 6. So this is a good example because it goes through and we can compare these two different methods of kinetics. Done.